Hello everyone, welcome back. Today I will be talking about vector and scalar quantities, and then in the next video we will do some exercise on those. So let's start from some definition, example, and exercise at the end. So what are scalars? So scalars are those quantities that are represented by a single number that can be with or without unit of measure, and they don't change depending on whoever is watching that observable. Okay, so they are independent of the observer. For example, temperature, if you imagine a cube of, an ice cube which is melting on the sun, and each time it will have a temperature which can be 0 degree until it's completely melted. And then of course this temperature, it doesn't depend on the direction from which you're looking at the ice, and of course it doesn't depend in the orientation of the cube of ice. If you change the orientation of the cube, the temperature is still 0 degree, and this is a scalar. Another example of a scalar quantity, if you can think about it, is a heater. So suppose you have a heater which is plugged to a socket, and the heater emanates some warmth air from many directions. And the power consumption can be 200 watts, for example, and this number doesn't depend on whoever is watching or wherever you put the heater. Wherever you place the heater in X, Y, and Z position, the power consumption will be 200 watts, okay? And the same goes with the energy, which is power times time, which is 200 joule for 1 second of 1 second. And those are scalar quantities. But also there are other scalar quantities that we will see later on that are important. Okay, so scalar can be summed together. Sometimes temperature cannot be summed, but the energy can be summed together and can be multiplied together, for example. Okay, so scalars are numbers with or without unit or measure. That's important. What are vectors instead? Vectors are quantities that cannot be represented by a single number in general. For example, if you have a point P, and if you are an observer here in point P2, we know that you cannot locate P1 with respect to P2 with only one number. You need at least two numbers, which is this distance here, which goes here, and the other distance here that goes here. And this is P1 x y, for example, and this is P2 x. You need at least two numbers to define the position of P with respect to P2. Okay, so the observer, and these two numbers will depend on the observer, of course, because if you look at another position, the point P, the composition of this point here will give you two different numbers, P prime 1x, P prime 1y, for the same number, for the same position P. So these are called vector quantities. I will tell you why in a sec, because you can draw a vector easily between these 2 points. And as you can see, the point is the same, but the vectors are different. Okay, v1 and v2. Force, position, acceleration, velocity are all examples of vectors, and it's easy to understand why they're vector, because we know that velocity is the difference of position over time, and position is a vector, so difference of vectors is a vector, as we will see. And acceleration is the difference of velocity over time, and again velocity is a vector, so the difference of two vectors is a vector, and divided by time is still a vector. And the force is mass times acceleration, so as we'll see, it's another vector. So we know vectors then can be needs more than one number, and they depend on the observer. But what is needed to define a vector then? To define a vector, we need a reference of frame of reference, sorry, because with a frame of reference we can uniquely define up to the observer the vector that we have in mind. And a frame of reference is defined by two directions, orthogonal direction, main directions, as I will show you in a sec. And then those two directions will be the rulers that you can use to define the vectors respective to that frame of reference. Let's do an example. So without a frame of reference, a vector is just, it has a direction, which is this line here, and then we place a length, which is this bit here. This is the length, and then it has an orientation, which is where it's pointing. Orientation can be pointing that way, or can be pointing this way, plus or minus, minus or plus. So there are three things: direction, length, and orientation. But as you can see, I draw these lines in a blank space, and it's different. It's very difficult to identify this line independent on something else. So what do? We define two directions orthogonal to each other, which is y and x. These are orthogonal direction because this is an angle of 90 degrees. And now we place this intersection of the two direction as 0, 0. It's a y2 coordinates because there are two components, x and y, and they're both 0. This is our center, where we put our eyes, the observer. And then at this point, the point here is a vector, but now it's easy to define the vector with respect to the component x and y, because we can take this direction here px, and this direction here py, and these are still 90 degrees. It's important. These are called projections. Px and py, and these are unique. They uniquely identify your vector p in px and py. But of course, this depends on the observer, because the observer share two directions, preferential direction, x and y. It's very natural when you walk around yourself, you give direction depending where you are. Up and down, left and right is depending where you are moving. And this is the same concept here. We place yourself here if you like, or the points where you want to get reference from. And this is a way to identify your vector closely, uniquely. Okay, so operation of scalars and vectors. So once we have a frame of reference, and we can define some operations between vectors and vectors, scalars and vectors, and this operation allows us also to understand how to decompose the vector in its component. In fact, a vector can be expressed as a sum of components over a particular set of vectors, which is called basis, as we'll explain in a sec. So usually those components depends on the frame of reference, but we know that we define a frame of reference, and then we can construct all the vectors based on that frame of reference. And then once we've got the orthogonal direction, we can find the components along this orthogonal direction, which will be the number that identify the vector up to the observer. Of course, those numbers will depend on the orientation of who is looking at the point, or the vector itself, but we can find preferential direction, which are called bases, which are observer dependent, and from which we can construct the components of our vector. And we will see this step by step in this slide here. So suppose we have a frame of reference O, where we have X and Y, and this is the center OO. Okay, and then suppose we have two vectors here, one vector over here and one vector here. So the first thing that we can do with a vector is to find the coordinates. Okay, so first thing first, define the basis. So we find two vectors, particular vectors, X and Y here, of length 1. And these vectors are particular because they have length 1 in only one direction. As you can see, this depends on the observer, because the observer define what is X and Y. But once the observer decides what X and Y is, those two vectors exist quite naturally. And these are vectors that will define all the other vectors, as we will see. Why is that? Because first of all, you can multiply a vector X times a number A, and then you find A times 1, 0, which is A, 0. And what does it do? This basically multiplies X times A. Suppose A is 5, 5A, A is equal to 5. So this is a new vector V, which is called 5x. 5 times x is, for example, 5, 0. And this is a vector here. And you can do the same with y. YB, B can be 3, and this is 0, 1, and this is 0, B. For example, B is equal to 3, if A is equal to 5 and B is equal to 3. And then you can see that the vector is multiplied by 3 times, and this is your vector V2, 3y. Okay, so we can definitely stretch this vector X and Y in order to make them longer. And then you can, once you have two vectors, what you can do, you can sum the vector V1 plus V2. How do you sum the vectors? V1x, V1y plus V2x, V2y. And then you do the sum component by component, V2x, V1y plus V2y. And this is not 11, but it's 1. And then you sum component by component. Therefore, you find another vector, which is V3, which is the sum of the two vectors. The sum can be also a difference. It doesn't matter. The sum can be a difference. So you can sum or subtract two vectors. Okay. So let's see then how we can find V3 as a composition of X and Y. We see that it can be easily written as AX plus BY. This is a standard way to write AB, which is AB. It's, since A is arbitrary and B is arbitrary, can be any vector. Can be this one here, or can be this one here. It depends on A and B, right? So these are all V3, V4, good vector. And these are all written in this form here, where you can see that the vector X and Y, which are these one, called versor if you want, are multiplied by scalar. This is a scalar, and they are summed together as vectors. And then every vector can be composed by these two ones. Okay, very important. So the composition, this is the composition of the vector in components, and A and B are the components of the vectors with respect to the frame of reference. But how do we find the components of a vector then? So the component of the vector, we have a vector V, we have the length of a vector, which is V1 square plus v1y square over square root. This is the length of the vector, the modulus, the length, which is the Pythagorean theorem of your vector p, for example. These are the components, px and py. And if you do the Pythagorean theorem over this 90 degrees angle here, you can see that the length of the hypotenuse is exactly v1 square plus vy square, which is the length of a vector p. But then there is another option, that there is another operation that you can do on vector, that is called the scalar product. Scalar product, which is basically given by the following formula, which is a way to find a number out of two vectors. So we have two vectors, okay? We have two vectors, and we call them v1 and v2, scalar product v2, and this is v1x, v2x, plus v1y, v2y. As you can see, these are the coordinates of v1 and v2, x and y, summed together. So it's a number, because the coordinates are numbers, multiplied together it's a number, plus two numbers is another number. So this is a scalar. But those are two vectors, okay? So it's a way to create a scalar number from two vectors, okay? As I will give example later on. So one way to extract the coordinate from a vector is very easy. You take the scalar product of a vector v1x times the vector x. Why is this is the case? Because this will be v1x times 1 plus v1y times 0, and this is 0. So this is v1x, because we're using this definition up here, 1, 0. So there is 1 and 0 here, the components of the versor. And this is the component of the vector in the x direction. If we do the same in v1y times y, we take the other component, of course, because in this case v1x times 0, because the versor component is 0, as you can see here, but the other component is 1. So we get v1y. And this is a nice way to extract the component of a vector. If you can see now, you can write v vector v1 as v1x plus v1y, which are two numbers, times vectors. Okay, as you can see, this is a way to compose vectors with vectors and numbers to create another vector. Okay, and this is a standard procedure to create any vector in the 2D plane. Bit more complicated in 3D, but it can be extended in 3D, in 3 dimension as well. Okay, so we just saw the vector decomposition in coordinate. So we have a basis, which is x and y, x and y. This is a basis. These are two vectors of length 1. This is a orthonormal basis because they are orthogonal to each other and the length 1. There are other kind of bases that are not orthonormal, but we're not going to talk about that one at the moment. This concept can be generalized as long as the two vectors that compose the basis have an angle in between. You can still create any vector out of those combination of the two. It's a generalization of what we saw before, but we don't want to go into this detail. We simplify our lives, and we also always consider orthonormal basis, which follow the Pythagorean theorem. Okay, we saw that. And from the orthonormal basis, we can get the coordinate of our vectors. Okay, x, y, and in 3-dimensional z, for example. Okay. We saw the scalar product. We want to highlight the scalar product as a tools to get meaningful quantities out of the system. For example, kinetic energy can be extracted 1 over mv squared. This can be seen as one scalar product of the velocity times itself, but also the work and the energy is force. This is a work the energy done by a force over a distance, scalar by displacement dx. This is the scalar product, and this is the scalar product as well. So all these are ways to compose vectors in order to get a scalar, which is a meaningful scalar because it doesn't depend on the observer. And this is very important. Usually scalar do not depend on the observer, while vector do. But then there is another vector that is called cross product. That is another product of two vectors, v1 vector v2, and this is called vector product, if you want, vector product. And it's written with an x, and this gives you another vector instead of a scalar this time. And the rule is quite simple. You have v1, and then you have v2, and then v3 will be a vector pointing orthogonal to the plane of v1 and v2, and his direction is the same direction as if he's rotating vector v1 towards v2. So this is the orientation that you have to consider. So you place your right hand on v1 and your thumb up in v2, and then you curl your fingers 1, 2, 3, and 4 fingers up in this way, and this is the right hand. Okay, so this is the v3, the component v3 is going upwards, and this is the direction from v1 to v2, okay, as expressed here. And those vectors are, for example, involved in any rotation. Whenever you have rotation, you have vectors. You have the vector product of two vectors, because the rotation is identified by an axis, which is exactly in this case v3, and the magnitude, which is the actual product of the two times the sinus of the angle in between. So actually v3 is v1 v2 modulus v2 times sinus alpha in the direction of, in this case, the z direction, because we have got z here in the z direction. Okay. Angular momentum, which is x times momentum v. These are maybe things that we will look in more detail in the future, but if you have a particle that is rotating around a fixed point P, and the particle M has a velocity V, you can define the position of the velocity x towards with respect to the point P, and then of course you can define x times v in a way that this will be pointing up the plane, and if you look at the let's say with a skewed angle, we can do it down here. This is the velocity v, is going this direction, for example. This is the point P, this is x, and then the momentum, the angular momentum, will be pointing up, and then the direction will be exactly the one that goes from x to v, which is this direction here, and it gives the rotation of the object around the point P In fact, this velocity is instantaneously rotating around this object, and the mass is just because this point has a mass. This is the momentum. Okay, this is just an example to say that you can combine vectors in order to give you another vector, not only scalar, but other meaningful quantities that do not depend on the observer are, for example, the one that are given by scalar product, like energy, work, the coordinate, the magnitude of an object, which are actually the magnitude of a vector. If we have a vector force, we know the magnitude is F times X times F square root. This is the scalar product, and is the magnitude of the force, which is independent of the observer. As we said, the energy is, for example, force times displacement, and this is independent of the observer, and it's a number, it's a scalar. Okay, so work, energy, magnitude of vectors, and things like that. And an example could be, for example, if you want to move an object uphill, this is an angle alpha, this is the direction x, over which you want to move an object, and the object is affected by the force of gravity, and then you want to move the object uphill by a direction dx. Of course, the only force that matters will be the one in the direction of the motion, because that's the friction that you're going to experience, and therefore the energy that is dissipated, or actually that is used, will be G scalar product X, and there will be the cosinus of the angle will be, we didn't say that, but when we have V1 times V2 cross scalar product, this is V1x V2x plus V1y V2y, but is also modulus V1 modulus V2 cosinus of angle alpha, and alpha is the angle between V1 and V2 alpha. Okay, so in this case, G times X, the alpha is exactly the angle that we have here, so will be modulus G, which is G, modulus dx, which is dx, times cosinus alpha. And this is the power that you dissipate along the direction. Of course, if the two are it's maximum when there is no angle, and it's minimum when there is 90 degrees, because the object is free falling, so there is no force that you have to apply in the direction of the motion, because it will be free falling. Okay, so I hope this is clear. We will give example in the next slides, but so today we discuss about scalars, which are numbers with unit of measures, and then we discuss about vectors as well, operational scalars and vectors, and some of the related quantities. So see you next time. Bye.